Welcome, Math Explorers, to another thrilling adventure in the world of mathematics. Today we are going to, as you see on my screen, we are going to explore reflexive spaces. But before we dive in, let's begin with a short yet vital motivation. In fact, I firmly believe that bridging the gap between abstract mathematical concepts and tangible real-world ideas is actually the key to enhancing our understanding. So that is definitely one of the main reasons why in all my videos I always try my best to make a concrete analogy. So picture yourself actually, in a hall of mirrors, and you see yourself reflected infinitely many times. Each reflection reveals a slightly different perspective, obviously, right? A unique angle. So reflexive spaces are like those mirrors. Instead of reflecting images, what they do is actually they reflect mathematical structures and ideas. They possess, they have a sort of mathematical self-awareness property, as they can actually look at themselves through the lens of linear functionals, offering thereby insight into their deepest mysteries. So let's start with a definition, right? So definition. Let E be a Banach space and let say J defined from E into E star star, the bijoule, be the canonical injection, be the canonical injection from E into the bijoule. So this means, remember how we define the canonical embedding was defined by at x you have d of x, and then it takes a linear bounded functional which is f of x. Of course, this f is actually an element of the Joule space. So the space E is said to be reflexive. So the space E is said to be reflexive. Let me put it in color. Said to be reflexive if the canonical embedding is surjective. So if J is surjective. So this means that the image of the space E is nothing else than the bijoule. So when the space E is actually reflexive, we often identify the bijoule with E. So maybe let me just write it. Okay, so when E is reflexive, we often identify the bijoule with E. So this means, you often write E is isometrically isomorphic. To E star star. Okay, So let's have some remark. Remark. So the first thing is to note that finite dimensional spaces are reflexive. Finite dimensional spaces are reflexive. Oops. Are reflexive. This is because this is kind of a short proof. Because if E is finite dimensional, then the dimension of E is equal to the dimension of the Joule space, which is of course equals to the dimension of the bijoule. Okay, so the second remark is that the very rare example, right? So the rare example of where E is actually isometrically isomorphic to the bijoule, right? But the canonical embedding is not surjective. So this means that, what I mean here is that isometric isomorphism is really distant from J. So that means isometric isomorphism so in fact, I think we have a famous author, famous mathematician, Robert James, right, who actually constructed a striking example of a non-reflexive space, which is actually isometric to its bijoule, right? Kind of funny. I think you probably put the link to to that research paper. So maybe I write it. So in fact, his name is, for those who are interested, of course, Robert James. So let me reconstruct it. Striking example of a non-reflexive space. By the way, a reflexive space is always a Banach space. So striking example of a non-reflexive space isometric to its bijoule. So I put the link for those who are interested, the link to the research paper. So again, as we shall see later, the upcoming lectures, of course, you will see that every Hilbert space is actually reflexive, and this is just a consequence of the so-called race representation theorem. And also LP spaces, right, for P actually strictly between 1 and infinity are actually reflexive. So our next result actually describes a basic property of reflexive spaces. So that is theorem 3.17, known under Kakutani. So theorem 3.17. This is Kakutani theorem. So let E be a Banach space. Let E be a Banach space. Then E is reflexive. So the space E is reflexive if and only if the closed unit ball is actually is weakly compact. I mean compact for the weak topology. If and only if the closed unit ball that we call B, right, which is defined to be the set of point x in E such that the norm of x is less or equal than 1. If only if this ball is compact in the weak topology, sigma E star. Good. So let's prove this proof. Of course, we start with the easier part, right? So we start with the simplification. So assume that E is reflexive. So assume E is reflexive, right? So this means the image of E is equals to the bijoule, right? So this means again that the image of the closed unit ball is nothing else than the closed unit ball in the bijoule. So however, we know that however, by the way, you can actually see E star star as being the joule of the joule. Okay, so however, we know from Banach-Alaoglu theorem, from Banach-Alaoglu-Bourbaki, theorem that the closed unit ball, the closed unit ball in the joule space, right, is compact in the weak star topology. It's compact in the topology sigma E star star E star. So therefore, I think it is enough for us, because remember what we want to show. We want to show that the closed unit ball in E is actually compact in the weak topology. So therefore, it is it is enough for us. It's enough to check that the inverse of the canonical embedding is actually continuous. It's continuous from E star star, right? And though with the topology E star star E star, right? Good. So the space E and O with the weak topology, right? Because if you show that J minus 1 is continuous, then from this relation here, right, what do we get is that, what do we get is that, and put it in color, we get something like the closed unit ball in E is actually the image of compact set, right, through a continuous map. And then we know that the image of compact set through a continuous map is actually compact. So, okay, so we just need to prove that J minus 1 is actually continuous. So, again, in view of proposition 3.2, right, in this proposition, I think we stated this proposition, I think, when we talk about the courses topology. So I strongly invite you to watch the video on the courses topology. I will put the link definitely, right, upper right corner of the screen. So in view of proposition 3.2, we only need, in order to show that J minus 1 is continuous, we only need to, we only have to prove that for every fix f in the dual space, right, the map which at say xi associate f, which is the dual pairing, right, so that this map is continuous on E star star in this topology. So, but this map here, this dual pairing, by definition is equal to the dual pairing of xi and f, right? And this map, the map at xi associate this dual pairing is indeed continuous. On the dual space, the bidual, right? So with respect to the topology sigma E star star E star. So hence, as I said earlier, the closed unit ball in E is nothing less than the pre-image of the image of the closed unit ball in the bidual, right, via a continuous map. So this is compact in the weak topology. So the first implication is done, right? So let's take a look at the reverse. So the converse is actually more delicate, and so the converse is more delicate and relies on the following theorem. Okay, the first lemma is actually call it lemma 3.3. Which is known under Helly. So this is Helly Lemma, right? So what does it say? Let E be a Banach space and let say F1, F2, Fk be given in the dual space. And let call it gamma 1, gamma 2, gamma k be given as well in R. So the following properties are actually equivalent to the following. Properties are equivalent. So the first one, so number 1, for every epsilon positive, so for every epsilon positive, right? So they exist on X, which obviously depends on epsilon. So there exist X epsilon in E, right? Such that norm of X epsilon is less or equal than 1, and the absolute value of the dual pairing Fi X epsilon minus gamma I strictly less than epsilon for every I moving from 1 up to k. So this is equivalent to number 2, put it in color, the absolute value of the summation over I moving from 1 to k of beta I gamma I less or equal than the norm, let me put it a bit, the norm of the summation over I moving from 1 to k of beta I Fi. So this is the operator norm, of course, and this holds for every beta 1, beta k element of R. Okay, so let's prove this. Proof. So proof that 1 implies 2, right? So fix beta 1 up to beta k in R and put it down, and let say call it X, right, be the summation over I moving from 1 to k of the absolute value of beta I. So from I, so from our assumption, right, from 1, you have that just rewrite the assumption, right, of that the dual pairing, you have the existence of X of epsilon, right? So this dual pairing minus gamma I strictly less than epsilon for every I moving from 1 up to k. So this means a triangle inequality. So this means the absolute value of the summation of beta I Fi X epsilon I moving from 1 to k, right, minus the summation over I moving from 1 to k of beta I gamma I is less or equal than epsilon times s. As I said, this is just this is just triangle inequality being applied. So and therefore the absolute value of the summation, I mean this is again the reverse triangle inequality that I'm about to apply. So the absolute value of this is less or equal than the norm of the summation of beta I fi. So this is the operator norm, right? And the norm of epsilon plus epsilon s I moving from 1 to k. So this is just the reverse triangle inequality, and also use the continuity of the beta I fi. So but this the assumption is less or equal than 1, right? So you can even further bound that term by the operator norm of the beta I fi I moving from 1 to k plus epsilon s. So now since this hold for every epsilon positive, right, we can make to make epsilon arbitrarily small, you obtain the second assertion. So you obtain two. So by making epsilon arbitrarily small, just can let epsilon goes to 0. Okay, so now second application, let's prove that 2 implies 1. So for that, well, put say gamma being the vector gamma 1 up to gamma k, the fx, right? This is a vector in Rk, and consider the map call it phi, defined from E to Rk by phi of x equals to the vector fi of x, right? I 1 from 1 to k. So property 1 actually says that, so you want to prove property 1. So property 1 says that, this is just to remind you of what we are going to prove or what we want to prove. So property 1 says that that gamma is an element of, belongs to the closure of what? Of phi of B of the closed unit ball. Let me just remind you of what it means. So this means being an element of the closure means that for every epsilon positive, right, there is this x, which obviously depends on epsilon, right, the closed unit ball, right, such that the norm of, so that phi of x epsilon approximate gamma, right, in the infinity norm, right? So this infinity norm means, since we are in Rk, this is the max of the absolute value of phi epsilon minus gamma I moving from 1 to k, right? So well, if the max is actually strictly should be less than epsilon, so this means all the elements should be less than epsilon. So this is phi of epsilon minus gamma I to hold for every I moving from 1 up to k. Okay, good. So this was just to remind you So let's keep it separate. Okay, so now this is what we want to prove, that gamma is an element of the closure of phi of the closed unit ball. So we aim to a contradiction. So suppose by contradiction that 1 does not hold. I mean that gamma is not an element of the closure of the image of the closed unit ball. So hence gamma on this closed set, right, may be strictly separated. This is where Rand-Banach second geometric form will be strictly separated. In RK, right, by some hyperplane. So this means there exists beta, right, which is in the vector beta 1 up to beta k in RK, and some say alpha in R, right, such that beta on the scalar product between beta and phi of x, right, strictly less than alpha, which is strictly less than scalar product of beta and gamma for every x equals unit ball. So this is scalar product, as I said, scalar product. So it follows, I mean, if you expand the scalar product, so it follows that this is just a computation, right, of the scalar product beta and phi of x. Phi of x is defined as being the vector of the fi, so of fi of x, I mean. So it follows that this dual pairing, the summation of I moving from 1 to k of beta I, well, let me put fi x, right, is strictly less than alpha, which is strictly less than the summation of the beta I, gamma I moving from 1 to k, and of course for every x in the closed unit wall. So, and therefore if you take the supremum over all the x in the closed unit wall, we get that. So, and therefore you get that the operator norm of the summation of the beta I fi I moving from 1 to k, right, slightly less than, I mean, it's just equal than alpha, right, which is slightly less than the summation of the beta I gamma I moving from 1 to k, as I said, by taking the supremum, by taking the supremum over all the x in the closed unit ball. So on the other side of the inequality, on the left side, you obtain exactly the operator norm. So, but of course, this actually contradicts the initial assumption. So which contradict? Two. Okay, so we are done, right? Great. So now let's state the second lemma, which is actually known as the Goldstone Lemma. So lemma 3.4. Goldstein. Okay, so let A be a Banach space. Right, then the image of the closed unit ball via the canonical embedding is dense in the closed unit ball in the bijoule. It's dense in B E star star. Of course, we need to precise the topology. So with respect to the topology sigma E star star E star. So and consequently, this is just a consequence of the above. So consequently, the image of the whole space E is actually dense in E star star in the topology sigma E star star. The proof. After this proof, we'll come back to terminate the proof of the Kakutani theorem. The proof. So let xi be in the closed unit ball in the bijoule, and let say v, right, be a neighborhood of xi, right, for the topology sigma E star star E star. So let's recall. So we must prove that the image of the closed unit ball via the canonical embedding actually intersect any neighborhood of xi. So this should be different from the empty set. But this is what we want to prove. So as usual, right, as we have been doing so far, so as usual, we may always assume that the neighborhood V is of the form V equals those are the neta in the bijoule, right, such that the absolute value of the joule pairing neta minus xi fi certainly less than epsilon, right, for every I moving from 1 up to k, right, and this is for, of course, for some finite family f1, for some given f1, f2 up to fk in E star and some epsilon positive. In fact, we actually saw in I think how to, I think it was actually in the video on the on the closest topology or the weak topology, or weak star topology probably, right? We saw how to characterize basis of neighborhoods of a point for the weak topology. So we may always assume that V has this form, right? So we have to find some. So what we want to do is that you have to, in order to show that the intersection is non-empty, right? You have to find some x in the closed unit ball, right, in E, such that J of x actually belongs to V. So let me write it. So you have to find some x, right, in the closed unit ball in E, right, such that put it here. J of x is an element of V. So being an element of V, this is again a recurve, so this means that Jx minus I, right, this is Joule pairing, should be less than epsilon for every I moving from 1 up to k, right? It's not visible, up to k, good. And this means, by definition, you know how we define the canonical embedding, so this means the absolute value of fi comma x, this Joule pairing minus xi fi should be less than epsilon, of course, for every I moving from 1 up to k. We know that J of x, this Joule pairing, J of x comma fi is nothing else than being the Joule pairing of fi and x. So okay, so put set say gamma I, right, just to be consistent. So set gamma I to be this Joule pairing between xi and fi. So again, in view of lemma 3.3, that was actually Helly Lemma. So let me highlight that. Just the previous lemma that we just proved. So it is it suffices to check that the norm of the operator norm, no, not the operator norm, operator norm here, because gamma I, that this norm of beta gamma I is less or equal than beta I fi I moving from 1 to k, right? But this is actually clear since we don't even have anything to prove, so which is clear since this summation of the beta I gamma I moving from 1 to k is equals, by definition, this is xi and this summation of beta I fi I moving from 1 to k, right? Because xi is actually is continuous, right? And also in the closed unit ball in B star star, so this is actually less or equal than the norm of beta I. So maybe I will write it like probably fully, right? So this should be less or equal by definition because xi is actually continuous, so this should be less or equal than the norm of the summation of the beta fi times the norm of xi. But remember, xi was chosen in such a way that its norm is actually less or equal than 1 because this is an element of B E star star. So this is actually kind of obvious. So we are done with the Goldstone Lemma. Good. So before going back to the proof of Kakutani theorem, right, the reverse side, so let's have a remark first. So remark. Note that that the image of the closed unit ball, right, where the canonical injection is close in the closed unit ball in the bijoule, right? This in the strong topology. In the strong topology. Well, just as let me just give you a quick proof. Indeed, show that it's actually close. We take the definition with sequences. So if say xi n, right, which is equals to g of xn, right, the sequence that converges to say xi. So we see that Sn is actually it's a Cauchy sequence, right? Because remember the canonical embedding is actually isometric. So Xn is a Cauchy sequence in the closed unit ball, right? Let me record the argument again since J is an isometry. So and therefore, because Xn is a Cauchy sequence, is a Banach space, so therefore Xn converges strongly to X, right? So that, and by kind of, how would I say that, by, I mean, we saw that, I mean, the strong topology is also is Hausdorff, and then we also have unicity of the limit. So therefore Xn converges strongly to X, so that xi is not less than g of X. So this proof that the image of the closed unit ball via the canonical embedding is actually closed in BE star star in the strong topology. So, but this, from this remark, it follows that, from the following remark, it follows that the image of the closed unit ball via J is not, put it in color, is not dense in BE star star, right, in the strong topology. Right, unless the image of the closed unit ball is equals to BE star star, right? But this property is not less than saying that E is reflexive. Okay, so the image of the closed unit ball, right, via the canonical embedding is actually dense in BE star star, in the closed unit ball in the bijoule, if and if E is actually reflexive. Good. So now let's go back to the proof of Kakutani theorem. So proof, just write it, proof of I think it was theorem 3.17. So proof of theorem 3.17 concluded Okay, go back to the proof. So let me just recall what we wanted to prove. So I mean, we proved already that E reflexive implies that the closed unit ball in E is compact in the weak topology, or it's weakly compact. The topology sigma E star. So now we wanted to prove the reverse, and then conversely, now assume that the closed unit ball is compact. In the weak topology sigma E star. So the canonical embedding, this is just a recall. Well, the canonical embedding J, right, defined from E to E star star, right? You should keep it in mind, is always continuous. From the weak topology into the topology sigma E star star E star, since every means for every, let me just write for every f in the dual space, the map ZX associate E of x, which is the dual pairing, like which is not continuous, then f of x, like, is continuous. With respect to the topology sigma E star. Of course, this is again in view of opposition 3.2. Okay, good. Since the closing ball is assumed to be compact, right, in the weak topology, so since BE is assumed to be compact, in the topology sigma E star, right, we deduce that and also, I mean, we saw that J is actually continuous, so we deduce that the image of BE via J is compact. And thus close in the bijoule, right, with respect to the topology sigma E star star E star. Good. On the other hand, by the Goldstone theorem or lemma. I think it was a lemma, yeah. By the Goldstone, by the Goldstone Lemma 3.4. The highlight. The image of the closed unit wall is actually, it's dense. It's actually dense in BE star star, right? For the same topology. Sigma E star star E star. So therefore, it follows that therefore it follows that d of BE is equal to BE star star. And this, because this hold, you also still have the image of E where J is equal to E star star. So this means E is reflexive. And with this, we actually conclude the proof of the Kakutani theorem. Okay, good. I think so far so good. Right? So in connection with the compactness properties of reflexive spaces, we also have the following two results, right? That we are not going to prove, but again, if you would like to get the proof of, if you face anything, any particular issue, please feel free to reach out to me, right, via email. We start with theorem 3.18. Okay, assume that E is a reflexive space. It's a reflexive space, right? And that, let me highlight reflexive, it's very important. And let Xn be a bounded sequence in E. Highlight bounded, so in E, right? Then there exists a subsequence say X and K, right, that converges in the weak topology. Sigma E star. So in a reflexive space, right, any bounded sequence has a weakly convergent sequence. The converse is also true, right? And namely the following. So the converse, let me just write it here. So the converse is also true, right? Namely the following. theorem 3.19. So this is maybe I write it here. Yeah. Eberlein. This is the theorem of Eberlein and Smulian. I'm not sure how to pronounce it. Eberlein-Smulian Theorem. So assume that E is a Banach space, right? Such that every bounded sequence, assume that E is a Banach space such that every bounded sequence has a weakly convergent subsequence, such that every bounded sequence admits a weakly convergent subsequence. And of course, in the weak topology, sigma E A star, right? Then the space E is reflexive. As I said earlier, right, we are not going to prove them, right? But I mean, in fact, the proof of theorem 3.18 actually requires an exclusion through separable spaces, which will be our target in the next video. However, the proof of Eberlein-Smulian theorem is, it's rather delicate, right? So, okay, so in order to clarify the connection between theorem 3.17, 3.18, and 3.19, I think it's actually useful to recall some basic facts. So remark. So number one, if X is actually it's a metric space, if X is a metric space, let me highlight metric space. It's very important. Right. Compactness is actually equivalent to say that every sequence in X has convergent subsequence. So the second remark is that there exist topological spaces, compact topological spaces. There exist. Compact topological spaces. Let me highlight compact topological spaces. Right, say X, right? Some sequences and some sequences in X, right, without any convergent subsequence. Without any convergent subsequence. So, I mean, a typical example of this would be, let me write it here, a typical example of such a space is, say, X equals to the closed unit ball in the dual space, right? Which is obviously compact, right? I mean, this is Banach-Lau glow, which is compact in the topology, the weak star topology. The weak star topology sigma E star A, right? This is by Banach-Lau glow Bourbaki, right? So when the set E is actually the space of bounded sequences L infinity, right? Which is I think it is easy to construct the sequence in X without any convergent subsequence. I mean, you can actually consider, the sequence, say, you take the Schroeder basis, right? Where you only have one at the nth position. So, I mean, for this sequence, you cannot, just writing, you cannot find subsequence E and K. That converges in L1 with respect to the topology sigma L1 L infinity. So this is not possible. Okay, so the last property is that the last remark, so if X is a topological space, with the property that, so you have a topological space with the property that every sequence admits a convergent subsequence. Slightly subsequence, right? Then the space X doesn't need to be compact at all. Then X need not be compact. So this actually only works in, if X is actually a metric space. Good. So now let's have some further properties of reflexive spaces. So proposition 3.20. Proposition 3.20. Assume that E is actually a reflexive space. Assume that E is a reflexive Banach space. I mean, there we need to say that it is a Banach space. So I assume that E is a reflexive space, right? And let say M, right, be a closed linear subspace of E. Then M is reflexive. Good. Let me highlight some important aspect in this proposition. So E needs to be a reflexive space. M should be a closed linear subspace of E. Okay, good. So if you have a closed linear subspace of a reflexive space, then M is also reflexive. So proof is rather simple. So first of all, note that the space M, right? So the space M, I mean, equip with the norm of E, or the norm induced by E, right? Has a priori two distinct Vic topology, two distinct Vic topologies, namely the first one is actually the topology induced by the Vic topology on E. So the topology induced by sigma E star, right? And also its own Vic topology. Let me drag it. Good. And its own Vic topology, sigma M star, right? But these two topologies are actually the same, right? Because so these two topologies, so these two topologies are actually the same, right? Since we say why. So since remember by Banach theorem, since by Banach, I mean every continuous linear functional, every continuous linear functional on M is, I mean, is just the restriction to M of continuous linear functional on E, right? I mean, we saw that if you give me a linear bounded functional on subset on M, I can always extend it to the whole space via the Hand-Banach theorem. So in view of Kakutani theorem, right, you have to check that in order to show that M is reflexive, in view of Kakutani theorem, you have to check in order to show, because you want to show that M is actually reflexive. So Kakutani theorem actually says that we only need to look at the closed unit ball in M. So you only have to check that the closed unit ball in M is compact. The weak topology is compact in the topology sigma MM star, right? However, or equivalently, we saw that this topology is just the same as the weak topology on E, right? So, however, as E is reflexive, because E is reflexive, the closed unit ball, this is again by Kakutani in E, is compact. So this is compact, in the topology sigma E is star, right? And M is actually, close in the topology. M is actually really close, right? Remember, let me put it in brackets. In fact, as M is a linear subspace, right? M is convex. And we know that convexity, right, plus strongly close, right? If you have a set which is convex and strongly close, then this is equivalent to say that the set is weakly close. So this is basically, the proof idea why M is actually close in the weak topology. So therefore, the closed unit ball in M is compact in the weak star topology. In the weak topology. In the weak topology, sigma A is star, right? Compact because closed subset of compact set are actually compact. So let's close subset of compact set in this topology. Good. So once M is reflexive, and we are done. So every closed linear subspace of a reflexive space is actually reflexive. Okay, corollary 3.21. Let's look at some of the consequences of that proposition. So corollary 3.21. The Banach space E is reflexive if and only if the Banach space E is reflexive if and only if its dual is reflexive. Good proof. We start, as usual, with the easier part. Probably not the easier part, but I think we start with the slightly difficult part, because both parts are actually easy. So assume A is reflexive. Right, and let J, right, to be the canonical embedding. Canonical isomorphism, right, from A into E star star. Isomorphism because J because the space is reflexive. So so we want to show. Let me put it. Let me write it. Right. So we want to show. So we want to show that the canonical injection say iota, right? Let's call it iota, from E star into E star 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 is surjective. So let me put it like this. Those is surjective. So this is what we want to show. Okay, good. So show surjectivity kind of objects, right? So let phi be an element of E star 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 be given, and put f, right, defined from E into R, Zx defined by phi is the Joule pairing, of course, dx. So f is obviously an element of the bijoule, right? And by definition, f of x, the Joule pairing is phi g of x for every x in E, but by definition again of the canonical embedding J. So, but by definition of J, right, you also have the Joule pairing between Jx and F is equal to the Joule pairing of F and X. So this means that we have phi, the dual pairing between phi and gx is equal to the dual pairing between gx and f. This holds for every x in E, of course. So since J is an isomorphism, so since J is surjective, right, as the space is reflexive, so we can infer that, so we infer from the above relation, so we infer that phi says xi, the dual pairing between phi and xi is equal to the dual pairing between xi and f for every xi in the bijoule, right? So this means that, so let me maybe I think this is iota of, no, not f, but yes, so this means iota of f comma xi, right, which is equal to by definition, is equal to by definition to xi f, right, is equal to phi xi. So this means iota of f is equal to phi, because the above relation holds for every xi in the bijoule. So we have proved that the canonical injection iota, right, defined from the Joule space into E star 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 is surjective. So, and then we are done. Now the reverse implication. So conversely, if the Joule space is reflexive, right, then from the first step, right, from the first implication, from the step above, we know that the bijoule is reflexive. So, and since the image of E through J is, is a closed, since this is a closed linear subspace, the image space, right? The image of E, right, where J is a closed linear subspace of the bijoule. So since J of E is a linear subspace, a closed linear subspace of the reflexive space, right? In the strong topology, of course. In the strong topology, we conclude, this was actually by proposition 3.20. We highlight that. So we conclude that D of E is reflexive as well. So therefore E is reflexive. In fact, if you have to, maybe like it, I mean, in fact, if you have, say, E and F, right, like two Banach spaces, right, and say T is a linear isometry, right? It's a linear surjective, very important, surjective isometry from E into F, right? Then the space E is enumerated. E is reflexive if and only if F is reflexive. So this is the reason why, from D of E being reflexive, right, we can conclude that E is reflexive directly. Good. So with this we end the proof. And now we state another corollary 3.22. I think so. Good. So let E be a reflexive space again. Right, and let K be a bounded closed and convex subset of E, right, in the strong topology, of course. Then K is compact in the weak topology, in the topology sigma E star. Proof is rather straightforward. So since K is actually convex and strongly closed, right, K is weakly closed definitely. Since K is convex, and close, right, K is weakly closed. This is theorem 3.7. We put the link to the video, so do not worry. So since K is actually convex and strongly closed, it is weakly closed, definitely. So moreover, K is bounded, right? So this means that there exists, say m positive, right? Such that k is contained into m times the closed unit ball in E. And well, since E is actually reflexive, we know that m times the closed unit ball is compact in the topology, in the weak topology sigma E star. Well, this is by Kakutani theorem. So now you have a closed subset of a compact set, right? Therefore it is compact. So hence K is compact in the weak topology sigma E star, right? Again, I call it as closed subset of compact set. So we are done. Okay, good. So let's have a look at another corollary, which is actually very important, right, for those who plan to, those having knowledge in optimization, calculus of variation, or PGs. So corollary 3.23, sorry. So let E be a reflexive space, right? Again. And let A be a non-empty closed and convex subset of E. So let's consider the map phi defined from A into minus infinity plus infinity included, right? B the convex lower semi-continuous for the strong topology, of course, function, such that phi does not blow up identically, and phi actually property 5-fold, so 5 actually goes to infinity as now of x goes to infinity. So put it in this column, and the limit of phi of x, the norm of x goes to plus infinity, equal to plus infinity, right? So if the set A is actually bounded, we don't need this assumption, so put it in brackets. So this assumption, right, is not needed, right? If A is bounded. Okay, so under the above assumption, then we conclude that phi, that is, it's its minimum on A. So this means that there exists, say, an x0 in A such that phi of x0 is less or equal, is equal to the mean of phi on A. Okay, proof. Fix A in R, right, such that phi of A is finite, right? Such an R or such an A, or fix A in A, sorry. Fix small a in A, right, such that phi of A is actually finite. I mean, such an A always exists, right, because phi does not blow up identically, so you can always find such A. So and consider the sublevel set, right? So consider the sublevel set. A tilde, right, which is the set of x in A such that phi of x is actually less or equal than phi of A. Then A tilde is close, right, convex, close, convex, and unbounded, right? So this is of course by 5, right, by assumption 5, right? So okay, so and there's A tilde is compact. Remember corollary 3.22, so that if you have a compact and if you have a close bounded and convex, we do not even need convexity, yeah, subset of a reflexive space, then it is actually compact in the weak topology. So there's A tilde is actually compact in the topology, sigma E is star. So this is by corollary 3.22. Good. On the other hand, phi is also weakly lower semi-continuous, right? In the topology sigma A is star. I mean, remember that we proved that phi convex plus lower semi-continuous or even continuity, right, implies phi is weakly lower semi-continuous, right, for this topology, of course. So it follows that phi attains its minimum on a shield, right? So this means there exists an x0 in a shield such that phi of x0 is less or equal than phi of x for every x in a shield. So you want to actually show that the minimum is actually attained on the host, on A, not on a shield. So let's prove. So let's show that. That phi of x0 is less or equal than phi of x, and this for every x in A. That x0 is not only the arc mean, right, on a shield, but also on A. So okay, so if you give me an element in A that is not in A shield, right? So you have, right, this is by definition of being in A and not being in A shield. So you have phi of x0, or which is obviously less or equal than phi of A, right? It's strictly less than phi of x. Again, as I said, this is just I don't know why. This is just a consequence of x being here. So therefore, phi of x0 is just equal than phi of x for every x in A. So with this we conclude the proof, right? So okay, so this corollary is actually the main reason why reflexive spaces and convex functions are so important in many problems occurring in the calculus of variation and in optimization. So with this we actually wrapped this video. So thank you and see you in the next video.